looking at exponents, order of operations, and averages. It's kind of a hodgepodge section 1.5, but they're things that we've been working our way to and around, and they're going to be important for the things we need to do. So we're going to kind of work through that. I want to highlight that in real numbers, wait, what did that do? There we go. I fell down here. That's why. That's better. 2 seconds here. I'm going to erase my board because things are in the wrong places. I do not like whiteboards. I think they're hard on the eyes on computer screens. That's why I use black. I think it's easier on the eyes. There we go. All right. So we're going to talk about order of operations, and most people have learned that as PEMDAS. I'll write it like this, PEMDAS, and if not, I'll explain things going through. Order of operations, you'll see me refer to over and over again because I look at it like a ladder, and these are the lower rungs of the ladder, and these are the upper rungs of the ladder. And notice there's two operations that are on the equal rungs. And you'll hear me say PERMDAS because exponents have a relative, just like multiplication has a relative with division, and addition has a relative with subtraction. And those are the roots. Exponents and roots reverse each other. Multiplication and division reverse each other, and addition and subtraction reverse each other. So I use PEMDAS as a way of remembering other rules because it puts things in an order for me. And we'll see this as we progress. So I will repeat it over and over again. But this order and these things have nothing to do directly with the concept of the quantity we're measuring, or as I said before, the property of real numbers. Property of real numbers is something we see in nature. When we use things that are real numbers, we see these properties. And there can be an argument as, do they exist without us inventing words for them? Or do our words make them manifest themselves? Right? There's a huge philosophical argument about what any of this means in the real world. But if we make numbers and real numbers, they have the properties. And they have both addition and multiplication have an identity, which is any number plus 0 is itself, and any number times 1 is itself. And what you're going to find as we progress is a lot of times we don't write multiplying by 1. It's implied somewhere in there that we're multiplying by 1, but we don't write it because, well, it's the same thing as it not being written there. They commute. Well, let me put the inverse first. They have inverses. So there is a thing that is a negative number that when I add it to its inverse, it equals 0. And there is a thing that is a reciprocal that when I multiply them, I get 1. These two things are related. Notice the 0 is in both of these and the 1 are in both of these. And I'm going to keep talking about these rules, and we'll slowly use them more and more. We're going to have to start digging into them a little bit. They commute, or we say they're commutative. And the root for commute is like if you're a commuter, you travel. And so that means that these things can travel. The order doesn't matter. If I add 3 and 2, it's the same as adding 2 and 3. If I multiply 4 and 5, it's the same as multiplying 5 and 4. The order in which we do them does not matter. And that's important that we note this is addition, that we cannot say the same thing for subtraction. They're associative. Right? If you have associates, they're the people you hang out with. And so I can by putting parentheses, say I'm going to associate B and C, which means I do them first. I add them first. But if I associate A and B and do those first, I get the same answer. And I can do the same thing about multiplication. At least multiplication writes smaller. And so these are properties, patterns we see in real numbers. If I take those quantities and I get them back down to tally marks, right? And then I take these new things we invented, addition and multiplication, we see these patterns with how those tally marks work. And then there's something that links them together, and it's called distribution. They're distributive. If I multiply something that I've added, it's the same as multiplying each of those things individually. And we'll see as we do more and more multiplications. Multiplications originally came from plowing fields. And so if I had two things that I wanted to find the area of, and I wanted to find the total area, well, this side is B and this side is C. So the entire length is B plus C. So if I multiply A times B plus C, I get the area of all of this. Well, I could also find the area of this rectangle, which has a width of A and a length of B, and the area of this rectangle, which has a width of A and a length of C, and add them together. And that's what happens here. And so that's where that distributive property comes from. We will explore these in more and more detail as we come through, but I'm going to keep referencing them so that we get used to these are the things that make all of the rules we're going to be talking about. And I'll be able to point to certain rules or certain tricks, right? We call them tricks, that satisfy these rules. In fact, a lot of part of early mathematics is making sure we can satisfy these rules to get answers more quickly. Now, what we have done so far is we have taken tally marks and named them as numbers. Let's see, 1, 2, 3, 4, 5, 6, 7. We gave it a name, so I wouldn't have to go through and count them up. And so it became, and we also invented this really neat way of having place values so that if I had a lot of tally marks, I could go, I think I did 24 there. If I'm off, will correct me. That there's 24. Well, I have 2 10s and 4 1s. The place has additional value for me. And by putting value in the place, it let us add and subtract and multiply more quickly. But by putting a little extra information in where numbers were stored. And then we said, you know what? If I'm adding together the same amount of things multiple times, so I'm adding 3 8 times, well, I can call that a multiplication. And so a lot of the tricks, or all these things we invented, multiplications and additions, and their reverses, subtractions and divisions, came about from we're counting things. In the end, I'm counting up how much stuff is there. But we want to say it in a lot less space. And we want to do it in a way that makes it quicker for us so that the predictions from coming about knowing how much stuff is around, yeah, and I use the word stuff a lot. You'll notice in the notes for today. I use stuff, and stuff. And for some reason, I think it's an old George Carlin bit about we have too much stuff that I get that stuff pronunciation when I think about it. So, because to me, the thing is, these patterns of numbers can be attached to anything, any stuff. But the pattern of the stuff needs some special way of talking about it. And so I try to accent the word so that we don't associate it with any preconceptions. So I'll use stuff and quantity a lot just to emphasize that I want to divorce it of any idea we have before pre-existing. And so instead of writing tally marks, instead of having them to count them up and state the number, we invented multiplication so that we can do that. And we invented addition, and multiplication is multiple additions. Well, exponents are multiple multiplications. I love saying multiple multiplications. I mean, I'm lucky if I don't trip up and stutter it horribly. Multiple multiplications. And so the idea would be, and we see this a lot in how things grow, in how cells divide. We even learned to count, right? Counting by twos. We learn trying to like we use exponents a lot when the same thing gets repeated over and over again, and counting by twos and counting by fives is an example of it. Counting by tens, and so when you have this counting, you can talk about how many times a certain thing multiplies through. So if I have a square, and to find its area, I have the exact same thing multiplied twice. And so I take that L and I take it to the second power. In fact, we actually call that squaring it. It means this is equal to L multiplied twice. And so this number up here is telling us how many, whoops, that bad me. There we go. That L squared equals L times L. And I wanted my 2 down here. We've multiplied it twice. So for example, if I have bathroom tile that's 6 inches by 6 inches, the area of that bathroom tile is 6 squared, or 6 times 6, or 36. And that's really how we introduce the idea of exponents. We're doing a multiplication over and over and over again. In fact, certain numbers have special words because they have a geometry, right? A square is the same thing multiplied by the same thing, so we call the power of 2 squared. Let's see if I'm good with my cubes today. Yeah, almost. If I want to find the volume of a cube, I have to multiply the length of each side, so the volume is S cubed, because the sides are exactly the same. So I have to multiply the length times the width times the height. And so if this were a cube on that tile, I would get 6 cubed, which is 6 times 6 times 6, which is 36 times 6, which is 216. So exponents became a way of talking about multiple multiplications. Notice what we've done though. We've taken addition, well, we've taken tally marks and we've given them names as numbers. That's our shortcut. We then took those names and used addition for a way of when we were gathering together multiple tally marks. Well, if we were adding the same thing over and over again, we turned that into multiplication. And when we take multiplication and we do it over and over again, we turn that into exponents. And so that invention of new symbols or new operations, operators we're going to call these, has addition being the first thing we do when we're repeating counting. Underneath it all is like counting, right? And then above that is multiplication, because multiplication is built out of multiple additions. And above that is exponents, which is built out of multiple multiplications. God, I love saying that. And if we want to reverse the process of addition, we do subtraction. If we want to reverse the process of multiplication, we do division. And if we want to reverse the process of exponents, we do roots. And so this ladder is how we invented these operations that we do. And that's why I kind of always remember PEMDAS as being this ladder. And you'll find knowing where you're on the ladder can help you. All right, so let's look at what exponents are, particularly, and how we name them. So we will say it's an exponent or a power. You'll find both words get used. And it is some base. Think of basement or bottom. And so I have the base to the power. And that tells me I'm multiplying b n times. Right? I put dots in there because I don't know what n is. It could be 500. It could be twice. And so it's telling me how many times I'm taking whatever that base is and how many times I'm multiplying it. Now, because of the identity, I want you to remember that I could multiply this whole thing by 1. Right? 1 times anything is itself, so we don't usually write the 1 out there. But a neat thing happens. If I am taking a base, any base to the 0 power, I have none of these. But I still have the 1. And so this rule kind of hangs underneath it all. Is anything to the 0th power is 1. And it's a little hard to see because we talk about how many times we multiply the same number. And if I'm multiplying it 0 times, well, what has to hide there? Well, for that to work, I need a 1 out front. Okay. Well, let's look at some examples here. So, if I'm talking about 5 to the 3rd power, or 5 exponent 3, that is equal to 5 times 5 times 5. I take the base and I multiply it 3 times. And 5 times 5 is 25. Multiply the other 5, and I will get 125. And so we're able to take our exponents and expand them back out to get an answer. We can also go the opposite direction. Sometimes we will get factors of a number that have a form. So 2 times 2 times 3 times 3 times 3 times 7 times 7, right? Some number is made up of these factors. Well, notice I'm multiplying the 2 twice. So I'll call that 2 squared. I'm multiplying the 3 times. So I'll call that 3 cubed. And I'm multiplying the 7 twice. So I'll call it 7 squared. The goal of mathematicians is to say the same thing in less space. You've already seen my handwriting. It's horrible. The less I have to do it, the better I can communicate it. And so, hey, I'm multiplying the same thing over and over again. Instead of expanding this out into tons of multiplications, let's write it compactly. And so that's what exponents do. Exponents compact what we're writing. I guess another neat thing that comes through here is if your base is 1, and I take that to a power, let's say 1 to the 7th, that's the same as 1 times 1 times 1 times 1, 1, 2, 3, 4, 5, 6, 7. 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1, and this is 1. So that's another neat rule of exponents 1 to any power is always 1. But we can do something like 13 squared. That's 13 times 13, which I'm going to have to do this out. 3 times 3 is 9. Nothing carries. 3 times 3 is 3. 1 times 3 is 3. 1 times 1 is 1. It's 169. Put that there. And so exponents let us do multiple multiplications. Well, there is a particular form of exponents that I've introduced you to, and now we can have an idea of where they come from. Because our system of numbers only has 10 digits, 0, 1, each of the place values can only represent 10 numbers, or we call it base 10. We call our number system base 10. So the ones place is 10 to the 0, because anything to the 0 power is 1. The tens place is 10 to the first, because that's 10 times 1 time, which is 10. The hundreds place is 10 squared, because that's 10 times 10, which is 100. And so exponents kind of underfill the place value system that we use. And this can continue. And so this is telling me how many zeros are after the number 1. When I have 10 to a power, that power is the number of zeros after a 1. And that's an important one that comes back up. There are certain exponents you'll find that we use, or bases we use, a lot as we move forward. Base 2 and base 10 are really popular. 2 because that has to do with how things multiply sometimes, and 10 because our numbers, we have 10 digits, and so that becomes useful. Okay, let's get some more exponent examples here, I think. I have 3 to the 7th power. That's the same as 3 times 3 times 3 times 3. There's 4 of them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Now I'm going to show you what happens in doing a long chain of multiplication. We tend to chunk out parts of it. What we say is, well, I'm going to associate these two things together. And so 3 times 3 is 9. And I replace those two with my association. Because it doesn't matter what we associate with in multiplication, I can associate these together, or I can associate these together. And so when I have really big powers, I'll grab all the same things together. I'll make little associations. I'm just using those properties of real numbers to simplify my multiplying. I don't want to do 9 times 3 and then 27 times 3 and keep repeating. Because now I have 9 times 9, which is 81, times 9 times 3. Well, I'll associate these together. I get 81 times 27. So 7 times 1 is 7. 7 times 8 is 56. 2 times 1 is 2. And 2 times 8 is 16. So 7, 8, 1. Carry my 1. So 3 to the 7th power is 2187, 2187. You can find by grouping, as long as these are all multiplications, then in the associative property lets you chunk it down. The way most people, when they first do this, is they'll look at this. I apologize. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And they'll do 3 times 3 and they'll get 9. And then they'll do 9 times 3 and they'll get 27. And then they'll do 27 times 3 and they'll get 81. And they'll do 81 times, and they'll keep working their way through. That rule of association lets us kind of put it into numbers that are a little bit quicker to calculate. But both will give you the same answer. And of course, as we go on, finding the key on your calculator. So on the calculator, 3, up arrow, 7 will also get you there. And so we'll use all these concepts to work. All right. Well, I keep dancing around order of operations, so I'm going to introduce what they are. When we write mathematics, it becomes important that we do things in a certain order to get an answer. I'm going to write this in bright red because this is going to be wrong. 2 plus 3 times 9 minus 1. Well, if I were just reading this from left to right, I'd go 2 plus 3 is 5. And 5 times 9 is 45. Minus 1 equals 44. Now, if we agreed that we would always read left to right, then this would be the right way. The problem is there's some ambiguity in what order you do things. And so remember, multiplications were built out of multiple additions. So mathematicians said, you know what? We're going to do things in an order. So the first thing we perform, and this is the order of operations, is we do things in grouping symbols. Do the things in the grouping symbols. And the grouping symbols we use are parentheses, square brackets, curly braces, and sometimes pipes. They have an opening and a closing. I have always visualized these as a bucket. And what the parentheses do is let me carry around whatever is in the bucket without worrying what it is. All right, so if I have 3 plus 3 squared minus 4 times 2, I see this as a something. And I'm having 3 added to that something. Well, I got to figure out what that something is first then. And so I come in here, and I do the order of operations inside of here. And then whatever that answer is, I add 3 to. And so I always look at parentheses as a way of carrying something around. And you'll find when you're trying to solve problems, you'll see it in my example for the kitchen counter problem. The length of one side I need to multiply by something, but I haven't figured out what it was yet. So I put it in parentheses. And what I'm saying is, I know whatever the length of this one side is, I'm going to have to use later, but I don't know what it is yet. So I'll put it in parentheses. And that's what these things are, is a nice little bucket. So we have to figure out what's in that bucket before we can use it first. So that's why they're at the top. The next thing is we raise any number to its power. And I'm going to put it here even though the book doesn't go into it, or take its roots. If you have a square root or a cube root. And we do this from left to right. So we do everything left to right, taking care of these things first. So looking at the one I did up above, I want to do what's inside the parentheses first. Well, inside the parentheses, the first thing I have to do is take the power. And so I get 3 plus 9 minus 4 times 2. Whoops. Ah! My pen! Ah! There we go. The third thing we do is we do multiplications and divisions. Again, left to right. So again, using the one up above, I'm still trying to get everything in the parentheses using an order of operations in there. Well, I don't do the subtraction first, I do the multiplication. So 9 minus 8. And now I can finish that. I'm going to get 3 plus 1. Because the last thing I do is additions and subtractions. Left to right. And 3 plus 1 is 4. This is an agreed upon way of doing the problems that we do so that we always get the same answer. You'll find with powers and multiplications, there are times when if you're just reading left to right, your answers can deviate. So, I ran out of blackboard space, so I will clear this. This is the time where in the classroom you would see me take my large eraser, walk back and forth over the board, and get covered completely in chalk dust and giggle, because I really enjoy my chalk. Alright, there we go, that's cleared. So let's look at one of these here, and I'm going to do the order of operations as I go through. So I look at this, and the first thing I do, and I will keep writing this off to the side. Please excuse my dear Aunt Sally. Whoops, that's not an A, that's an M. And I'm going from top down. So I want to do parentheses first. Now inside the parentheses, I reevaluate this, going top down. And so the first thing I need to do is the power. Now it is good practice to write each step you do in mathematics on a separate line. So if you make a mistake, A, it's easy to fix, and B, it's easy to find. So a lot of people will jump to just write down the answer, But it's a good habit, especially as this gets more and more complex, is to do it in step by step by step. Mathematics, if you notice, I'm overemphasizing, we counted. We turn counting into names. We turn names into additions. We turn additions into multiplications. We are taking a lot of little steps and bundling them into bigger things. So when we do things that have a lot of steps, we should be clear about those steps so that those quantities become, or the process becomes evident for us looking back. So doing the parentheses first, I will write everything outside of the parentheses the same. And the first thing I have to do is my exponent inside of it. So 4. So I've only done one of the operations. I've rewritten it that it's equal to what I wrote before, but I've only done one of the operations. Now I have to do this multiplication inside, and I'll keep the parentheses here to illustrate something. So 4 times 36, I'll do that over here. 4 times 6 is 24. Carry the 2. 4 times 3 is 12, plus the 2. 144. Now a thing to note here is when we don't have a symbol, we have a number next to a thing, right? The parentheses is a thing. Mathematicians assume that's multiplying, right? You're going to see again another thing I want to say is mathematicians hate to write things unless they have to. So we don't need to write the multiplication sign because these two things next to each other we're going to say is multiplying. So I need to do 144 times 3. 3 times 4 is 12. Carry my 1. 3 times 4 is 3. Carry my, well, it's 3 times 4 is 12, plus the 1 is 13. Carry my 1. 3 times 1 is 3, plus the 1 is 4. So that's 432. And then plus the 7 gives me 439. And that's how our order of operations works for us. It's a way of working our way through the problem and letting the relative value of the operation tell us what to do first. The things that are more complex build out of lower things, the exponents, we do first. Multiplication, because it's built out of additions, we do before additions. And additions are counting the bottom rungs of our ladder. There's one more thing I want to show about it, and it's assumed parentheses. Some of our symbols in mathematics get overloaded and used for multiple different things because the thing underneath it is very similar to what we're doing. Next chapter, we're going to be learning fractions, and fractions are based off of division. So the symbol for a fraction bar is also used as division. In fact, that's the symbol for a ratio, which are where fractions come from. That's the symbol for a fraction, right? I have something like this. I'm dividing something like this. Well, if I take this symbol and I mix it with that symbol, I get our division sign. It's really where it came from. This was used mainly to talk about ratios. This is used to talk about fractions. And this is used to talk about divisions. These are all a language difference on how we use it. To the quantity, they're all the same things. And so a weird thing happens. I'm going to show you this problem as it's written. Now notice I have no parentheses here, but this division bar separates this into a top and a bottom. So really, we have parentheses on the top and parentheses on the bottom. This top we have to treat as a thing. And that's the nature of using a fraction bar as division. And that pops up a lot. We could write it like that. I find as I've matured as a mathematician, I don't use this as much unless I'm talking in an education standing. Most of the time, things that come out of work, you tend to see in it with the fraction bar as a division. So when you see me do examples, I'll tend to write them like this. You ask me questions, I'll do them like that, and we'll go from there. All right, so I'm going to do this then. I'm going to do what's in the fraction bar first. I'm going to change colors, and instead of illustrating a point, I'm going to do this step by step so we see how to record our steps. So my order of operations says do parentheses or grouping first. We're going to say, hey, that fraction bar or that division sign grouped the top from the bottom. So I need to figure out what's up top there. So 44 minus 36 is 8. Now, PEMDAS, let me write it down here again. So I've done my grouping. I've now got to do my exponents. Well, I have an exponent here. So I'm going to rewrite that as 5 times 9 minus 8 times 2. Now I've got to do the multiplication and the divisions. Well, I have a multiplication out here. And I have a division out here. And then finally, I do my addition and subtraction. 45 minus 4 is 41. So PEMDAS gives us the rules to communicate these quantities using these operations in an order. And that order is based off of how we develop those symbols. If I were to give you a quantity, PEMDAS would not naturally come out of it. It's something people had to invent to talk about the patterns in quantity. And that distinction will become proper because I will keep returning to the properties of real numbers. And those properties are patterns that we see. And because those are patterns that we see, there's certain things we can do. The rules are how we write and communicate. And that distinction will come out as we do more and more of these. We're just starting this journey, right? And I'm trying to point you down to some things that are gonna keep propping up, and they'll get a little more complex and a little more complex. So be aware of them now. But for us right now, we want to do that PEMDAS. We want to do the grouping symbols first. We want to do the exponents, and we want to multiply, divide, add, and subtract.